Welcome back everyone, and we're back with more WebGL 2.0. So today we're going to go back to armatures again, and we're going to do some more stuff. But we want to start getting animations for Bendy to be imported into our website. So to do that, we need to start adding more functionality or more parsing functionality to our GLTF parser. So we're going to go through a little bit of the spec, look at what it looks like, look at the code and how to parse it, and bring it into a more developer-friendly data structure, because the structure they kind of provide is kind of messy. I personally don't think it's developer-friendly. It's just, I don't know, it's kind of a pain in the ass, it's kind of a mess, for me anyway. And, we're just going to parse it out, make a nice structure out of it so that we can kind of use a little bit of it. And we're going to animate this little object. So we're going to try to pull out all the information to use the armature on this rig simple example and animate it based on that. And we're going to have a little fun with the animation too. I'm going to add a little spin to it at the very end so we can have some fun. So GLTF. It's a pretty decent format, what I've read so far, because I never really had experience with FBX or Collada. But I've heard that out of the three formats, is probably the better format. The only problem with GLTF right now is that the Blender plugin exporter isn't fully baked yet. It's still missing some features. It can only export one animation at a time. Only the active animation. It can't export custom normals. That's, I put a ticket up for that specific problem because I need custom normals to do something with Bendy. So I had kind of had a lesson planned, but because I can't get the data out of Blender, I have to kind of postpone it and do other things, and hopefully get to it when that plugin gets some of those bugs fixed, and hopefully the animation stuff will be added too. So this is really, there's not too much to the animation part of the spec. It's all JSON inspired. We have animations, the name. Let's look at the code, because this is kind of all spread out and kind of hard to see. So let's talk about the spec a little bit. So this is what a channel, or this is what all the animation is. This is what it all looks like, right? So it kind of starts off with animation. Animation exists at the root level with nodes, skins, and models. So it'll be which one of those root level elements that you can pull out. Each animation might have a name. Our test one does not. So this would be, if you're exporting from Blender, those are called actions. So this will be the action name. The name. So this way you can walk, run. So, and it's an array. So since it's JSON, this is an array. So this is all one animation set. So inside the animation array. Now you have channels. I don't know why they call it channels. Going through GitHub, I've read that people sometimes call these kind of tracks. What these are, I kind of write notes for myself because it took me a while to kind of get it, because the naming convention is a little wonky to me. Like I said, since other people call it other different things. A channel connects the node in our node list to a sampler. So this channel points to node that lives in the node's root level, and it connects it to these things right here. So what type of node it's pointing to? It could be any node. And don't forget, a node in WebGL GLTF, like I said, this is our second video on parsing GLTF. The first part we did, or probably the first two. I made two. I think I had two so far, right? Yeah. I think first one was getting the mesh data. Second video was about getting all the skeletal data, I think. and now we're trying to get all the animation data. So that's the thing we got to deal with. So node can be anything. It can be any mesh, it could be any joint. A node can be a light source, it could be a camera, it could be a lot of things. They kind of just throw every object in the nodes array, and it's kind of a pain in the ass because it's a little messy. That's why I consider this very messy. I would wish, like these, like I said, literally can point to anything. It could be an object because you can. I guess the whole point of this animation is that you can animate an object. It's not just joints or armatures. You can animate the rotation of an object, or the translation, the scale. And this also, I forgot what the fourth thing of animation is. It's the, I forget what it's called. It's when you have like a bunch of vertices that creates one object. Morphing. There you go. Morphing. So there's translation, scale, rotation, and morphing. So those are the four things you can basically sample to transform. So morphing. We don't do any morphing. It will be a long time before we get to that point. But it's only certain reasons for morphing, like talking. You do morphing for talking. Morphing can also be for transforming a body a little bit. Having like a very thin body to being a fat body to a muscular body. You can kind of create these blends between the three. That's what morphing does. You take the exact same vertices, but you move them around to make different shapes, and then you can use morphing to kind of go from one point to the next to the other. So that's what morphing is. But like I said, we're not going to be doing that. Not for this. But this is the main three we're going to deal with: translation, rotation, and scale. And for us, we're even going to be using scale because armatures don't really animate scale. So, and the parser function I did is only for armatures. I'm only pulling out armature information. So when I'm looping through the channels, I'm looking for just joints, not anything else, because that's all I care about. So basically, it's going to tell us the node, the object that we're going to animate, and we're going to tell it what part of it we're going to animate, and that's all this thing does. And sampler contains an input, how to interpolate, and the output. Now this kind of screwed me up because I thought this was something else in the beginning. Reading the documentation, it took me a while in reading the documentation several times over again to realize what these things are. So in sampler, excuse me, the input is the time that this translation happens. So if this is pointing to sampler 0, this is sampler 0 because it's the first element in this array. Excuse me. Oh my lord. I lost my bottle. Oh my god. I'm thirsty. Alright, so sorry about that. So that's the time, and the output is what value that's going to be. So if since this is a translation, so if it's like at time 1 second, and oh, by the way, all animations are based on seconds. And oh my god, and sorry, oh my god, the air's too dry. It's getting colder, so it's getting difficult to talk and breathe sometimes. So it's time, and it's using seconds, and sadly, fungi uses milliseconds. So for us, we kind of have to upconvert all our second information into milliseconds. I don't know if I should convert everything back down to seconds, but then I have to use a bunch of floats. With milliseconds, I can do everything with integers. So to each their own, right? Okay, so output contains the what's changing, and input is when that change happens. And the interpolation gives you how we're going to go from point A to point B. And there's several different types of interpolation functions, and most often you're just going to do linear, and the other possibility might be slurp, but slurp is not on the list. I don't know if one of these are like the other name for slurps. I haven't really used these before, so I'm not exactly sure what kind of curvature these create. But if you can, this might be just a cubic. This is the yx cubed. Since it's a cubic spline, maybe that's what it is. It's a cubic curve, which that would kind of somewhat be like a slurp type of interpolation, I'm guessing. I'm not sure. Like I said, I don't know what this one is, this specific curve or step. I'm not exactly sure what step is either. So yeah, so let's look at some code. So first we're going to get a reference to the animation, since the JSON is all rendered. And we're going to check to see if there's a name. And if there's no name, we're just going to give it a name and the index value. So it's anime, 0, 1, whatever the index of the animation. Because we kind of pass in the index we want. So in the test, a lot of the test objects for animation, they do something kind of bad. And if you ever go to GitHub issue tickets, you'll find some people really complaining about these samples. Is that for every joint of animation, an animation set is created for it. So instead of saying run and then moving all the joints of the skeleton to animate it for that run action, you'll have run bone 1, run bone 2, run bone 3. So you have to loop through all these animation sets to actually animate, and that's a problem because that's not how applications do this. You have one animation set and all the bones are animated within that one set. I think they said it was just really to show you the testing, how multiple animation sets, but in my opinion you should just make 2 animation sets, one walking, one running, not put 1 bone per animation set. It's kind of aggravating because that's not real world use of especially when it comes to armatures for testing. So it's kind of a pain in the ass, but like I said, it's just for testing, and then once we get this working, we're going to be just using Bendy for the rest of the series when it comes to animations. So we just need to know how to parse it correctly. So if you're going to use a sample stuff, don't be too concerned when there's some issues with them. So like I said, we got the animation name, and then we just start looping through the channel, because the channels, they're just the things that connect everything. That's right. I had like a brain fart for a second. I don't know why. So it's late. It's like probably midnight already. So so we're gonna get a reference to the channel that we're currently rendering, and the spec specifically says if there is no node defined in there, just exit. So it's required. It's every target has to have a node. That's right here. Target. It always points to a node. So I don't know why they even bother calling it target. Maybe they just probably just call it node, unless there's other use cases for target. I don't know. For all I know, maybe they'll point to something else. And then since remember when I'm there's some issues with the data, so I have to go and kind of fix the data a little bit. So when I go through skeletons, I have to go through all the nodes and make sure I mark the ones that are joints as joints, because sometimes if you go through I kind of forgot, but there's when you're kind of looping through, there's actually extra nodes thrown in there that shouldn't be there. They're not actually joints. So if you're just going to process them in face value, then all the nodes, you'll actually probably start bringing in things that are not part of the armature joints. They're not armature joints. So fixed skin data kind of does that. It kind of just compares and makes sure everything, and then it kind of just marks it as a joint. Another problem with this is the new change I added right here, because another thing I have to fix when it comes to dealing with animations is that let's see, like this points to a node, but these nodes, especially in this sample, have no names. So it points to a joint, but the joint has no name, so it's just nameless joints. And when I was trying to hook them up to get to animate, that's a problem because I need to know the name of the joint to animate. So because to use the sample data, like I said, that those sample they have up there, they're just, a lot of them are kind of crappy. I guess those are the worst case scenarios. So you use those to make sure your encoders or your importers don't break. So yeah, so this new line of code for fixed skin data, if the name is not defined on a joint that I'm marking as a joint, if it has no name, just create one. So it joint and then the index value, because since I'm looping through the skins, and I'm going through the skin and just going joint by joint. So actually, yeah, I loop through all the skins, every skeleton that's in the file, and just fix them up, because like I said, the joints need to have names, and if it is a joint, it needs to be marked as a joint. So this way, when I'm looking through skeletons and other things, they don't get all screwy. I think that's the only big change I did here. I think so. So that's why here we need to make sure it's a joint and make sure it has a name. It needs that. We need that for animations. So like this function probably should be parse skeleton animations, because this parser is more meant for skeleton animations, not regular animations. So once we have that, since we know our channel, we're going to get its sampler value. So this way we're going to point to the sampler, and then I'm going to show you. And once we have the sampler, we have to get the data. Now you said, I remember it says time. The thing that really screwed me up with the spec is that I thought this was timed. Like, man, what is this, 5 seconds? I thought it was like 5 to 6 seconds, but no. This points to an accessor. And in an accessor, am I saying this correctly? Accessor. Yeah, I guess it is an accessor. An accessor is, like I said in the previous video, is just information on how to parse all the binary buffer data to pull out the information that you want. So sample input and sample output actually goes to the accessor array that's inside the file and grabs that specific accessor, and that one gives you the information and tells you where in the buffer the information is. So this is what we're doing now. This function already pre-existed from previous videos. I don't need to explain it. So we just tell it what accessor we want, and it gets all the information out. So here I have that information outputted, and I have it nicely put together. So for parsing, let's say the translation. So let's say we're parsing this channel, right? So we got this channel. We know that's the 0 channel. That channel goes to that sampler. So it goes to that sampler. So I know to get the accessor number 5 and accessor number 6. So accessor number, and I know it's joint 1. I got the name. Let me see. So the target is the node, and the node goes to, oh no, actually never mind. Yeah, when I get the reference to the node, which is right here, I know its name, so I can actually output the name of the joint I'm currently accessing. So T is for time, V is for value. So this is the time. There's our accessor data value function gives us some information, tells us how big a chunk of data is and how many there are. And there's 3, but only 1 component length. So there's 3 separate bits of information here. So, and this is T data. So this is time. So from the accessor, from the binary buffer, we're pulling out these 3 floats. And this is time. So our timeline, the first keyframe on our timeline starts at that time. So it's 0.04 seconds. The second keyframe is 1.04 seconds. And the final keyframe in the animation ends at 2.08 seconds. So that's the time. All right. And then we go to the other accessor, the output accessor. We have a component length of 3, and we have 3 components in general. So this 3 creates the first component, this 3 creates the next component, and this 3 creates the next component. Now you'll see 3 bits of information. Like, well, what's this for? Well, this chunk of information is for translation. So you get 3 components, so you know this is a vec3. So you got a vec3, and it's for translation. So it's translation information. So what's changing is the y. But in this instance, the value is exactly the same. So the animation for this translation, there is no animation. The value stays the same throughout the timeline. Now, I don't know if there's the default value, or it is the default value. So it's really not animating. I wish the exporter would exclude anything that's not really animating. If there's no value that has changed from the start, probably don't bother putting that information in there. It's kind of a waste to actually pull all this information out and to realize that data is worthless. So I kind of hate that the spec kind of just throws everything out there. So at some point I might have to write code that actually checks the timeline and makes if every single one is the exact same value, just exclude this whole joint from the animation stack, because it's worthless. It's no point in processing it if there's no point, like I said, there's no point in processing this information if it's not being used for anything. It's not animating. So in this example, it's wasted. It's a lot of wasted information. Now rotation will change. It's the same time, same keyframes, and component of 4, and there's 3 of them. Component of 4 and its rotation. So these are all quaternions. So that's the second second keyframe. The first and third keyframes are identical. So it's kind of like you start in A, you go to B, and then you end at A. So you kind of create like an infinite loop. So that's what that animation is for, that rotation for joint for the and scale. There's no change in either one. But like I said, I'm not animating scale. I'm only when it comes to skeletal armatures, all we need to do is mostly rotation, and every once in a while we need to do some translations. So that's the data that's being pulled out from the accessor, and all we do is kind of just fix it up, and in this part just creates a new data structure. That's all it does. That converts all this information into something a little bit more easier to read than this. Like, this is how the data looks like ideally when it comes from GLTF. So if I comment this out, we can see the structure that I'm making that's easier for the developer. So if I comment out this one, at the very end, I'm to refresh. So this is the structure that the parser is creating. So creates a struct, and it gives you the name of the animation, and it gives you all the joints that animation does. So joint 1, here's we're going to deal with just rotations really. So we're going to click on rotation. So we have joint 1, and then inside it we'll have more properties. We have rotation. So for joint 1 and its rotation, we have linear. So we know how to interpolate. And then we have samples. So I created a something samples under rotation. And for the samples, I set the time and then the value that changes. It's already a float vec4. So it's a quintorian. So time and quintorian. And these are the samples. So the time and the values are together, where before they're kind of two separate things. So this way it makes it easier to kind of loop through, and so if like this structure might be developed further. So the idea is that you can go say, okay, I want keyframe 1, and I can go through all the joins and all the individual components and get keyframe 1. So keyframe 1 would actually be, let's say, yeah, this keyframe. So I'll get that one because I know what time it starts, scale. I can go into the scale, get the samples, and also get the first one. So this way I have the time and I have the value that it's supposed to be there. And that's not, this is very clean animation, but other animations might be more complicated. Some values, I have to see what the output looks like, really, in all honesty. But when you look at it like through Blender animation, you can have keyframes only modifying one thing, or you can have keyframes modifying several. I don't know how that will be exported in GLTF because I haven't done it yet. But I'm assuming it's just going to throw everything out there. I'm hoping it kind of just only throws out there what needs to be inside that file and not have all that garbage. This one has a lot of garbage. Like I said, scale and translation doesn't animate. It's the same values for every single keyframe. It's a waste. The only animation is rotation. So all that data gets converted into this. So we only have one joint, and each one is broken down. I don't know if, to me, it seems like the most rational structure. I don't know if it's the most efficient structure. But when I build an animator, maybe I'll see that this is not the right way to do it, and I'll change it. Or I might keep this as is and then use this to import it into the animator, and the animator will convert this into the actual format that makes more sense for the animator. And that's probably the better idea. Like this should be like the simple format for developers in case you want to use this code for your projects, but you're not using my animation structure that I end up creating for the animator. So like I said, this is just make it developer friendly, so you can actually get the information out really easy. And in the end of the day, like when you're done with the GLTF, like if you're gonna, it's smarter to kind of resave this back out in this format or whatever format that's easier for you. GLTF, TF part is the transfer. Is it the transfer format? I think that's what it means. So the idea, or transport format, it's called the transport format. So the idea is that it's just transporting the data. It shouldn't, ideally, I guess it shouldn't be how it's always saved. It's just a way to get information from Blender and into your game engine. That's it. Once it's in your game engine, you should save it into what's most optimizable, most optimized for your game engine. Your own specific non-documented structure. Unless you do document your structure, like I'm doing now a little bit, and use that for your animation object. But yes, and that really is all to it. That's it's not a lot when it comes to parsing. Like I said, it's just taking all this information and just kind of grabbing it, pulling it apart, and then putting it back together in a different structure. So it's easier to see and read and whatnot. So right now, there's no animation being done. So I want to just do some things. I just want to say I changed something in quintorians. I added this line of code. Let's see, that would be lerp, because we're using lerp because we're gonna animate the bone a little bit. So inside Quintorians lerp, because when they do the modification, it wasn't saving the is modified because it's a static function. So if it sees that it's not it exists, it sets it to true. So this way, when I do an update, it automatically does an update because we only update the data when it's dirty, if it's been modified, to save time on the CPU. And the other change I think is armature, and this was just to make sure there's names. So load GLTF file. So this part is just really just to check to see if the name exists, and if the name does not exist, it gives it a name. I did this first, then I end up fixing the data itself. So this way the data always has a name for it. Because if I have a skeleton and I have an animation, I can't marry them together using index values because there is no index values when it comes to nodes. The way the structure is kind of a pain in the ass. So the easiest way to connect an animation on joints and a skeleton's joints is just to compare the names. So if the names match up, then you can easily say, okay, this animation information belongs to this joint over here. So that's why I'm enforcing names. The names have to exist. And even though I'm doing this, everything loops in an array when it comes to the skin value. So the joint value names will match up, even though I'm just making a name up and just say joint and the actual index of that joint that's in the skin part of the file. So those are the only big changes. If you're following the fungi development, just do those small changes, and you're good to go. I'm sorry, guys. I've been waiting for a couple of days to do this video, but this cough won't go away. So you can look at the rest of the test file. There's nothing really much changed. I took out a lot of stuff from tweening from the previous video, and it's a lot simpler. So we're just kind of just loading in our rigged simple and our armature stuff. This is just all regular. This is mostly from the armature animation for bendy when we're animating bendy. So this is really just that file. So we download, we parse the mesh, and then we parse the animation. We got the animation. We don't need this anymore. And we want to animate. So I have a quat here short for Quintorian, and I'm going to save the starting rotation of that that joint specifically, because I'm going to animate that one joint. Remember, we're going to do this animation, which is that one bone that kind of just bends a little bit. It's just rotating a little bit. So to do the animation, I need this to have a starting point because I'm going to blend between each stage. Let me get some more water. It's hard to do these videos when I got allergies or whatnot. I know I brought a cup up here. I can't find it, so I have to drink everything out of my gallon. All right, so we're going to set up a very, very simple animation loop. Super simple. Dirty simple. So we're going to base it on time. So we got 3 seconds. We're going to take those 3 keyframes and spread it out to 3 seconds of animation. So SS. So SS is times since start. So we're going to use that and do a modulus on 3. So this way we can kind of divide that time based on 3 seconds, so we know where in 3 seconds we are. So this way, no matter what, like a modulus, it always creates a value between 0 and like this value would be like 2999. So we take that value and then we divide it by ms. So this way we kind of normalize the value. So once we have the normalized time value, we divide it by 3 or times 3. So so once we have normalized time, we're going to say, well, we want that normalized time, but when so based on that time, which keyframe am I going to be using? So that's that's basically all this math is. I'm converting all this time to know what keyframe am I currently using, and I'm using floor to get rid of all the fractions. So ideally, with 3 seconds and 3 keyframes, I'm kind of dividing each keyframe by a second. So, so let me actually uncomment this, because we're going to need to see the data again. So now that I know what keyframe I'm at, so I'm going to take the joint rotation, and I'm just going to get the sample rotation data of that specific keyframe. Yeah, so if I'm going, so if I go here, see, now we're going to completely ignore time because we're making up our own time. So when it's between the in the first second of animation, we're going to be using this data. We're going to be using that float, or not that float. I'm sorry. We're going to use this quaternion rotation. On the second of an animation, we're going to use this one, and on the third, we're going to use that one. So we're kind of just going through these 3 keyframes, 0, 1, 2. And it works out because I keep going back to this file. I don't want to go back to here. And then, so we're just going to copy that animation value into our joints rotation and do an update. So that little fix to quaternions, no, that doesn't do it for here. But yeah, ignore what I just said. So we're just going to copy the animation data for that specific keyframe we calculated, and we're going to update the armature. We're going to say, okay, we just updated one of the joints, update all the world matrices of the armature to get it ready for animation. So with that in place, oh my god, snooze. If we refresh, there we go. Now we're going to refresh again. So you go 3 seconds of animation. Dun, 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 dun. So those are the 3 keyframes. Remember I said in the first it starts at A, it goes to B, and then goes back to A because that's the starting position. And oh my god, it keeps going back there. And you can always change the time. So if I want, I can just say 1 second of animation. So 1 second of animation is going to be divided up amongst 3 keyframes. Keeps going back there. See, now I sped up the animation. Now it's switching keyframes. But this is kind of boring. This is really bad animating. Oh my god, I'm probably have to close this, so it's out of the way. All right, so like I said, this was dirt simple animation loop. So we used animation data that we parsed from GLTF, and we're applying to the thing. Now we got a much better animation loop. Now, we've done this math before, so because my voice is starting to fall apart, I'm not going to bother explaining it too much. I do have comments here, so it helps if you guys just want to read it out. So the idea is that we're still going to figure out the time for our animation, and we're going to figure out which keyframe that we're currently in. So, it's the same thing as up here. So, figure, and then on top of that, we're going to. So let's see how to explain. I want to explain as quickly as possible. So all this math is basically trying to find the time, normalize time, spread it around the 3 keyframes, figure out which keyframe we're currently on, then start interpolating to the next keyframe, if I remember correctly. Oh no, it's not interpolating to the next keyframe. Interpolating to where we save. Remember in the very beginning, I said I'm making a copy of the starting quaternion. This is why we're doing this. So we're going to start here. This is going to be our starting rotation. And so when our animation begins, we're going to go from our whatever our current or whatever our starting our starting rotation is, and we're going to work ourselves toward the one that's animating. So we're going to interpolate from point A to point B instead of just going from A to B, like teleporting like we did in this simple animation loop. We're going to actually do the traveling from A to B back to A. So that's why we can figure out what time, and then we're going to also figure out the time in between the keyframes. So as we're traveling from keyframe 1 to keyframe 2, what is the time between the two keyframes? So we're gonna get that like up here we do floor, so we get rid of that little fraction. We're gonna use that little fraction here. We get it back this way. We get that little fraction back. So, and we keep track of which keyframe we're currently in. So that's why that's what index is. So I'm starting with a keyframe value that doesn't exist. So every time we finally hit the time for the next keyframe, we're going to copy the current rotation, and then the next keyframe we're going to interpolate between that saved value till we reach that keyframe, and we're just going to keep going. So when we reach the next keyframe, save that current value, and then interpolate to the new keyframe that we're moving forward. So we're going to, that's what we're doing. And we always lerp between our saved quaternion and the keyframe rotation value, and we're just going to apply it to our joint rotation. And IT is the time, that little fraction between frame 1 and frame 2, or between frame 2 and frame 3. It's that time between the two frames. So once we do lerp, and lerp is short for linear interpretation, so we're going to lerp two quaternions from point A to point B, and if we refresh, now you can see the animation is not popping. It's actually smooth. It's interpolating from A to B back to A. And there you go. And now we have a much better animation loop. So I'm not going to make a full animation object right now. That might be another video down the line, which is going to be a lot more smarter. Where it has to handle more it has to be smart, where it has to take all the bones and joints. Like right now, this is all the code to animate a single joint. So this needs to be done on a loop, where you're going to update all every single joint. So it needs to be a little bit bigger, a little bit better. Now, so we're going to have a little bit more fun before we finish up the video. So, like I said, this animation is kind of boring, right? And if you remember, things like that. Here's easing. Remember the last video we did easing, and easing is a curved value. It's a graph value that creates curves, and it's also a way of interpolation. So if you want to say linear, this is a linear curve, or a linear interpolation. So if easing is a form of interpolation, we can take this value and dump it into an easing function. So I selected elastic out. Elastic out is pretty cool. So if we're going to do elastic out, so we calculated that linear. So that's what the IT is. It's really our linear time between our two keyframes. So we're going to dump that value into our easing function, and we're going to get a new timeout that is going to be based on this curve. Elastic out. Where's elastic out? And this one. So it creates this animation. So it's boing at the very end. Yeah, and like remember the parabolic? Yeah, the parabolic curve, y equals x squared. So so we're basically putting in x it's going to do something to X and it's going to give us Y, and that's what's going to happen. So if I say this using our easing, remember last video we did easing and tweening, we're going to use just the easing function, not the tweening. Refresh. Now I'm interpolating between the keyframes, but instead of using linear, I'm using easing or elastic out. That's what I'm using. I'm using that as the interpolation equation for it. So there you go. Boing, 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 boing. There we go. That's all we're doing. Now it's got that nice spring. Now it looks better. It's not just this. You know, it's got some smoothness. It's got that spring. So we can you don't always have to use linear. You can use any kind of easing curve you want to interpolate between your values. So if you wanted to have if you want to add a little spice to animations, like if you have bone animations that you're importing, you can just use easing functions to add a little extra spice to it. You know, so everything's all linear. You can add more. You can add spring to it. Let's see. Let's try one more. Tween. Let's see. I don't know what's a good one. Let's see. What looks like a good animation? Nah, it's not fun. Oh, how about that's just insane. Let's try something like that. Ease in, out, bounce. I'd probably put under bounce. Ease, bounce in, out. That's probably gonna make a really bad animation. So let's give it a shot. Let's see what this looks like. Actually, not bad. That's kind of like let's say if you you have a robot and he's trying to move his leg, but it's kind of broken. It's like a damaged bone, like a damaged robot leg. That's what the animation looks like. But it's kind of interesting that we take this simple keyframed information, just throw in some new easing functions, and we can make the effect different. So you can really play around with the bones in your animations. You can really tailor it. It's something you can't do when you're doing a game engine, really. But if you're building your game engine, you can kind of add. You can actually play with it a little bit. That's why I'm not a big fan of Unity, because you can't modify things. I think with Unreal Engine, the source code is open, so you can kind of tweak it. You can add your own things. And Godot, the open source game engine, it's open source. You can do whatever you want with it. So this is kind of fun. Yeah, it's damaged. It's got this kind of damaged looking kind of animation. Here I thought it was going to be something bad, but it's actually pretty neat. It's fun to experiment because you never know what you're going to get. Ease in, bounce. Bounce in. Let's bounce in. And bounce in looks like it might be good. Let's try one more. Bounce in. No. Just one more before, because you know, like I said, it's fun to experiment. I don't want to waste you guys' times. Let's just see what this looks like. I really don't know. I'm just really messing around right now. Yeah, it looks like I said, it's kind of like damaged. It's trying. It glitches and falls down. Like if you're gonna have, I can see this being like some kind of old factory. And you kind of have maybe those mechanical arms, and they're trying to move, but it's all glitchy and broken because everything's kind of falling apart. So you can do like this. You can kind of program your own animations. You don't have, you can. All you need is just a couple of linear keyframes. A, B, C. You just go to a couple of keyframes and just use easing to really just create the actual effects for you. I think if you're going to actually create this effect with keyframes, you'll have a bunch of keyframes. You got to animate to position rotation A, you got to do rotation B. So ideally, this animation would be a lot more complicated data-wise, but just by using an easing function, we just made it more efficient, more optimized. It's better. It's all mathematical instead of having a bunch of information that we're kind of just processing. We're only processing 3 keyframes, but this animation that's being generated is probably several keyframes worth of data, but it's kind of being just calculated as our interpolation function. So that's it for this video. We parse all this information out. We're actually making simple animation loops based on the keyframe information, and we explored customizing the animations by using our own easing function instead of just using linear or the other 4 options that GLTF says that you can use. Like I said, screw everyone else. If you're building a game engine, you can add extra things into there because, like I said, this is very efficient. It's 3 keyframes. I don't even need this animation to be coming out of GLTF. I can set those 3 keyframes myself and hard code it somehow and just have the easing function handle it for me. So you don't even have to parse all that data. It's kind of a waste of time to produce like a pretty good animation if that's all you're kind of looking for. So it's that's what I love doing. I like learning how to code and do everything mathematically and not have a tool do it all for you. It really expands your knowledge. It really gives you a sense and understanding how all this works. It gives you the ability to do more than the other guy. Like this is what I always try to say when it comes to why I'm doing this. I don't want to be another Unity developer. I want to be the guy that can build Unity. And if you're here watching this, that's probably what you're aspiring to. You don't want to be another guy who just finished doing a Unity tutorial, online course or something. You want to be the guy who can walk in saying, "Oh yeah, that piece of those little systems in Unity. Yeah, I can build those. No big deal. I know how to build an armature system. I know how to build an animation loop. I know how to do all those. I know how to do a bunch of those effects. I don't need to just press buttons and Unity does it all for me." So I don't want to knock Unity. Like I said, Unity is good. It's gotten a lot of developers and a lot of cool games out there. I'm not knocking it. If you want to make a game, I've said before, if you really want to make a game, just use what's available. Because I've been doing this for it's December. I've been doing this for almost a whole year, and I'm still I'm not ready to make games yet. Like I'm still trying to get armature bones. I'm still doing other systems to make a game engine work. So it's like one person, only a couple hours a week. It's been a year. I'm not even at a point yet where I can really start making the kind of games I want. So this is not the way to go about if you want to make a game, especially as an indie. So but again, this is more about knowledge. Like maybe my goal is really to build a game with my own engine. It's not be the best game. Like I'm not gonna even bother selling. I'm just giving it out for free. And once I have all that knowledge, I'm probably gonna pick up like Unreal or Godot and then make a really good game. But at that point, I have all this knowledge. I understand how all this works. And by using those engines that are open, that I can modify the source code, I can just use it. If I don't like something about it, I can just change it because I already know how to build a game engine from scratch to begin anyway. At that point, 10 years from now, because I'm such a pessimist. So yeah, what time is it? So I wasted guys too much of your time. So yeah, I hope you're enjoying this. This is kind of fun. Our poor little broken robot leg is not functioning very well. It's just tweening. Next video is going to be another system video. We're going to go back to FBOs, and because I wanted to do a specific effect, I wanted to create force fields, and I can't build force fields without accessing depth buffer, and I can't access the depth buffer because it's not built into Open or WebGL. To do that, you have to build deferred rendering. So I built deferred rendering. I got that, do I have Imgur open? Oh no, that's right, Twitter. I use Twitter now. So I think I posted that this morning. I got this finally working. Next video, we're going to work on building up the deferred rendering, multi-sampling, and I'm probably want to do some post-processing effect with the all-in-one video, because we've done FBOs before, so I'm just adding an extra couple of bits into it, and I updated the API so it's easier to use. And then the video after that, we're going to create this effect. So this is going to be 2 videos from now. So the next video will be kind of more of a system thing, and then we'll create this effect after that, which is it's called intersection highlighting. This is all done with shaders, but it requires depth buffer. So I have like a green force field, and then it kind of creates that little I don't know. It just highlights where the intersects. So it's kind of like, so I want to make this cube kind of animate, so you can kind of see where it gets highlighted where it intersects the force field. Like, if you've ever seen like Star Trek, like the old the Next Generation series, and you see a ship going through the force field, it creates that little effect around it. Since it's going through it, it's kind of loud to go through it, so it's kind of touching the hull of the ship. I'm creating that same effect in WebGL. Like I said, it took you have to build a couple systems to get this to work right in WebGL. Like, I've seen this effect in Unity, that's why I wanted to do it, not realizing that OpenGL does not give you the access to the depth buffer. You have to kind of create your own depth buffer, your own custom depth buffer to do this. So yeah, so hopefully, and then so I got some really cool stuff that lined up after this. I still got to do more armatures. I got to build the animation system. So that's all the stuff that's coming up soon. Like I said, if you're really interested, you can follow me. It looks like I got another follower. You can follow me on Twitter. You'll see my progress. So I'm starting to use that to kind of show off things I'm currently just finished, or where I'm kind of working on, or I might have some complaints. I don't know. So yeah, so I may know people. So yeah, that's it. I'm tired. So yeah, I'm really excited. I can't wait to get to this video, because I think you guys are gonna love it. The video after this, we're gonna actually make a real force field with using a sphere. That's gonna be hilarious. That's gonna be great. If I can build anything like how Unity does it, how people have done it with Unity, you guys are gonna have a field day with it. It's gonna be an awesome effect, and Bendy is gonna come back, and he's going to have a force field, and Bendy's gonna have a nice little, hopefully an animating force field. But like I said, that video is gonna be about just building the prototype effect, and then we're gonna use the effect to actually do some fun stuff. So yeah, like and subscribe. I'm now on Twitter, so you guys can see me there. Got my Patreon. I know Patreon's changed their crap just recently. I don't like the fact that they're going to push the fees onto the patrons. In all honesty, I'd rather them pay the fees onto me, because it's not fair for you guys. They're trying to make it fair for, I guess, the creators, so they keep more of the money. If you guys are willing to give me cash, and there's a new Patreon I got. I'm sorry. Thank you very much. I don't know your name right now. Maybe you don't want me to put it on videos, but yeah, I'm on the side of, I'd rather take the fees from the total cost. You know, if you guys give me like $5, if the total fees are like $1, then let me just keep the $4. You know, I don't want you guys paying the extra 30 cents just to give me $1. I think that's not fair. So I'm on that side when it comes to the Patreon debate. I think most creators are on that side. I really hope Patreon changes the rules, or leave the rules as is. Let us, the creators, kind of handle it. You know, we'll take the hit, because, like I said, in the end of the day, it's it's you guys that contribute that really helps everyone out. You guys are the ones that really help, that makes a lot of not my content specific, but just everyone else. There's a lot of people that that that's their main income. I would love this to be my main income. If you guys can make it happen, I would be so doodly grateful. But if I can quit my day job and do this every day, I would do it. I just need to make enough money. But until that day, I'll just do the best I can. So this month you'll see more videos from me because I do have a month off. I don't want to go into too much detail, but I have a month off from work, and hopefully everything's all right. The month I'll go back to work, and if things are not all right, I'll be making more videos more often. Yeah, Merry Christmas to me. Like I said, I don't want to go into too much discussion about that, but yeah, this month I'm going to spend more time making videos and coding, because now I kind of have like 8 to like 14 hours a day, depending on if my wife and kids need me to do stuff with them. So any time that I'm not being the father or husband, I'm going to be working on this stuff. So I'm gonna have a lot more time this month to really, like, this system stuff took me 3 days to do. If it wasn't for me having time off, this stuff would actually take me a month, not 3 days to do. So yeah, hopefully there'll be some good stuff coming out this month for you guys, because I was able to do more complicated effects and systems and get things done and move fungi along, so we can start hopefully making some games sooner than later. So yeah, that's it. Like I said, I just can't wait to get that. So like and subscribe. Subscriptions help. Likes, I guess, help. I'm not sure. I'm still new to this YouTube thing. And I really just prefer coding, and that's it. So if you guys have any suggestions, or if there's any specific effects that you're very interested in, please comment. Tell me what you guys like. Because like I said, I've been eyeing this force field effect for like months, and now that I have time, I'm doing it. So you guys get the benefit, because there's actually, I have not been able to find this effect in WebGL. And I understand why now. It's a pain in the ass to do it. It really is. It's a really big pain in the ass. To build it from scratch, it's a real big pain in the ass. But it's well worth it. I can't wait till I do the spheres. So, like I say, if you see any effects, send them my way. If they're really cool, I'll probably try to implement them. All right? So, yes, like, subscribe. See you guys in the next lesson about FBOs and depth buffers and whatnot. Bye-bye.